Hello, everyone. We're back for day 19. So today I'll be attempting the last medium tree problem here, and then we can move on to other parts of the map. Today is a Monday, February 3rd at 12:46 p.m. After this, I think I'll do a couple priority queue problems and a couple backtracking ones. I always see a lot of stuff that needs priority queues and heaps, so I'm really looking forward to that. And same with backtracking. I feel like that's another thing I don't quite understand that well. But anyway, so today for day 19, we'll be looking at this problem. I have not looked at it yet. Construct binary tree from preorder and inorder traversal. So we get two arrays and we have to make a binary tree. Okay, so I haven't really done anything like this one before, so I'm guessing it's gonna be a little tricky. Okay, so we get two lists of integers, which are the values where we want to create a node. And we want to return the root. Okay, so preorder, pull up paints. So preorder is root, oh god. It's roots left, right. So preorder is root left, right, and in order, that's the other one, right? In order? Yeah, in order is left, root, right. So let me just do it myself first. So if we get 1, 2, 3, 4 in preorder, then that means it would be 1, 2, wait. Would it be like this? No. One, two, three, 4. 2, 1, 3, 4. Okay, so it would be like this instead. Roots left, 1, 2, right. Okay, yeah. So if we look at this subtree, we do root, left, and then right. So we do this subtree, and then we do root, there's no left, and then we do right. So how to construct this tree? Couldn't you also, are there multiple trees? Like for instance, if you have 1, 2, 3, 4. No, I guess not, because you would do root and then left. Oh wait, no. Yeah, this one would also be it. Right? So if I have this binary tree, we start with this subtree and we get roots and then left. So we analyze this subtree and then we get root and then left, root and then left. Yeah, so I think is there not several ways to do it? Okay, so for in order, so I'll just keep that there. Whoops. For in order, if we have 2, 3, 1, 4, couldn't this also work? Binary tree. Oh, I see. It has to work with both of them. Oh, okay. Okay, okay. So this is the only. So this tree, 1, 2, 3, 4, is the only tree that works for both of those arrays, right? So this basically tells you which one goes to the left. I mean, yeah, this one seems kind of tricky. I don't know if I'll be able to do this. I just don't have that much experience building trees. And especially, we have to combine both of them. So I could start by just populating just like top down, I guess. So we could say like node equals tree node with so I'm thinking what I want to do is first build a node that points to null, and then build another node and have the left part be equal to this, or the right part, maybe depending on the traversal. So in this case, we'd build one, and then our next one is 2. Should we start from 4? So should we build 4 and then 3 and then 1 and then 2? And then we have to do oven. I wonder if there's like a math. 2, 1, 3, 4. So this tells us the root of the tree. Okay, so that gets us somewhere. So we can use this. So we know that everything here is on the left and everything here is on the right. And then can we like recurse that somehow? Is there any more examples? Let me just okay, so we know this is to the left of this one, and this is to the right of this one. But we know when the root is based on this. So do we have an algorithm that's just like, so we have 2, 1, 3, 4, and then we know the root is 1. So we start by creating 2. And then we know the next one should be like greater than this one. So we could put it here, but because we know we haven't found the root yet, we put it here. So yeah, we essentially have 2 options here. So we could put one here in the blue, or we could put one here in red. And both of that would fulfill this. Okay. So maybe at this point, so these are the only two places we could put it. So maybe we can use the preorder. And we know that 1 is the root. So therefore it has to go up here to the blue. Okay, and then our next one is 3. So 3 being greater than this, we could go here in orange, or here in green. Okay, so now in this case, we've seen, we have, okay, I think I'm getting somewhere. So in this case, one is after, wait. So we're here. So in this case, when we decided to put 1 here, we've already seen 1 before, so therefore it's above. But here, when we encounter 3 at the same time, maybe because it's at the same time, then we put it after. Okay, so I'm just going to keep track of what we see in preorder. And then if we see it, so if I have like, I don't know, I'll just make up, I wish there was more examples for this one. I think that would help me. So let's say 3, 4, 2, 1. And 1, 2, 4, 3. So let's say this is pre and this is in. So we know the root is 3. So what I would do is for in order, okay, so I'd start with 1, obviously. And now 2. So 2 can either go here or here. And then we'll do like a visited set. So we've seen 3. So that means 3 is above this. So we haven't seen 2. So I'm going to put it here and see if this works. Okay, now 4. So now I guess we've seen 4. So 4, we could put either here or here. So we could put it either one. So we've seen 4, so I'm going to put it here. Okay, and now we've seen 2. Now 3, we've seen 3, so I'm going to put it here. Now we've seen 1. Okay, and now let's see if this tree matches. If this tree matches both of these. So preorder, we start here. We do roots, and then left, so then we analyze this subtree. 4, and then left, so we analyze this subtree. 1, 2, 3, 4, 1, 2. And for in order, is left, root, right. So we start here, left, then we go here, left, there's nothing, root, right, so 2, and then we go back up, 4, 3. 1, 2, 4, 3. Okay. So it did work with this example. So basically what I did is if we've seen it before, then that means it's above us, I believe. And if we haven't, then it means it's below us. I don't know if that's true, if I got lucky. But let's maybe try programming it for now, because I don't really know where else to go. Okay, so we're gonna have a I counter while I is less than length. So they should be the same length, right? Same size, okay. Length of preorder. Okay, so what we want to do every time is create the node. So we'll say node equals tree node with, and I'm using the in order values. So we'll say in order of I, which is a value. So this will create the node, and then we can either, so we kind of need, so at any given step, so if I backtrack a little bit here. So for instance, when we're deciding where to put 3, we need access to this node and this node, because those are 2 options. Always. Because if we're going to the right of in order, then it means that has to be below it or above it. So maybe I can say like below and above, which will be the 2 nodes that we can reference. So in the first example, we'll just set it to in order of I. And I also want to have a visited set. So we have below and above right here. Okay. All right, so then we'll go to 2. So 2 is not invisited, so that means we will put it down here. So below, so we create a new node, 2. Okay, so if it's not invisited, we create a new node. Well, okay, so we create a new node. We always are going to create the node no matter what. All right, and if it's not invisited, then we want to set below dot right equals node, like that. And then below equals node. So we essentially make this connection and then say that this node is now B. Okay, so there we go. So now we added 4 to the visited set. And we go to 4. So 4 is invisited. So we create the node, and now for 4, we say node.left equals above. So this node's left pointer goes to above, and then we make above this one, and then we say above equals node. All right, and then we add 2 to visited. And I'm just adding 2 to visited because we have like corresponding eyes. Okay. And now for 3, so we create the new node. And 3 is invisited, so we're going to make the node's left pointer to above, and then move above here. And I think we just return above. Okay. Whoops, sorry about that. And And then, so every time we make a node, or I guess we could just say visited.add preorder of I. And then return above. Oh, below is integers. So this is just a value. So how can I initialize? I guess I could say if not below and not above, and set below above equal to node. Okay, so we got a tree, so let's trace it for here. So we have 1, 2, 3, 4 for preorder, and 2, 1, 3, 4 for inorder. Okay. So first I'm going to create 2 as a node. And it's not invisited. So do we send it to itself? We don't want to do any of this. Okay, let me try it, the algorithm first and see if the algorithm actually even works on this example. And if it does, then that means there's a problem in the code. Okay, so first in the algorithm, we create a 2 and set below and above there. Then we go create 1. Okay, then actually, so we add 1 to visited. So we create 1. So 1 is in visited. So that means we set the pointer like that. And to make this above. Okay, and now in visited we have 2. Okay, and now 3. So we create a node 3. So 3 is not in visited. So we put 3 here. And then add it to visited. And now 4 is not in visited. So we'll put 4 here basically. So we have a tree that's 1, 2, 3, 4. Okay, instead it should be 1, 2. So 3 should actually be here. Yeah, so actually I guess when you have, well, let's think actually. So here, in this case, there's 2, so when you create 3, the node, there's, and in your visited set is 1 and 2. So when you create 3, you can add it here or here. So we should have added it here. So I think maybe what we could do is add the visited set, add it to visited like instantly. I think that would work. Well, if we add it to the visited set immediately, I think the algorithm does work for this one. Okay, so we add 1 to visited, and then we put 2. Alright, and then we add 2 to visited, and we put 1. So 1 is not in visited, so we put 1. Wait, 1 is in visited, sorry. So we put 1 here. Okay. Then 3, so we add 3 to visited. 3 is in visited, so... Oh, Oh, okay. So in this case, 3 needs to be... Okay, so this tells you what's below each other. And this tells you if it's to the right. So you're always adding to the right. So actually there's a lot of places you could add 3. So you could add 3 up here. It's not just 2. You could add 3 here. Or you could add 3 here. All of these mean, well, I don't think this is true actually. We know 2, so we know 1 is greater than 2, so that's fine. But 3 has to be greater than 1 and greater than 2. So it can't be here, right? Or can it? So this means it's greater than 2, but it does mean that it's less than 1, so it can't actually be here. So it can only be in one of these two positions. So maybe before, with the algorithm, you don't actually need a below pointer, because it can never, you can never actually add it down here, because it has to be greater than this thing that you've already added. So maybe instead the question is actually between these two positions. Okay, so because 3 is invisited, then we add it to the bottom. And then for 4, so there's 2 places you could add it now. So 4 you could add, so it has to be greater than everything. So you can add it here. That makes all of this less than. If you add it here, that also works. You can't add it here, because then it would be less than 3. And you can't add it here or here because it would be less than 1 and 2. So you do have 2 spots again. So I think you do need... You actually do need that pointer. So you have 2 options. You can make it the new root and put everything to the left, or you can add it as the rightmost element. So then you have B, and then we know we've seen 4 before, so that means it's not higher, it must be lower. So then we get this tree, 1, 2, 3, 4. Okay, so I'm noticing, so when I start the algorithm, so okay, we have it on the whiteboard, so now we have to code it. So what I always do is first just create the node. Then can it be empty? No, okay, so if it's 1, so I create the node. So let's just say node equals tree node with in order of 0. And then we say above equals node and below equals node. Like that. So we put above and below right here. Okay, and we can set I equal to 1, I guess. And we also want to say visited equals a set containing node. No unique values, right? Okay, so we could just add its value. So we don't need any of that. Okay, so we create the new node. This is a bit of a problem. Maybe we could create the node down here. And I don't think we need this. So, all right. So we create a new node. Oh, actually, this is fine. Yeah, this is fine because we still have access to above and below. And we're creating of I. So, okay, so I starts here now. Okay, so the first thing we do is for in order. Okay, so we add, so visited already has 1, and now we add 2 to it before we do anything. And now we create a new node 1. And node is in visited. So, okay, so if we think about it, there's 2 options that one could go. It can become the new root, or it can become after. So because we've already seen it, that means this is the root. So we say node.left equals above. Like that. So node.left equals above. And then above equals node. Okay. And then I plus equals 1. I plus equals 1. So now we add 3 to visited, this one. We create 3 as a new node. Just putting it anywhere. It is in visited, so okay, so there's 2 places we could put it. We can make it the new root, or we could put it here. So if it is in visited, it says below dot right equals okay, so what it's doing now is it's saying put 3 here, which obviously we don't want. So I think maybe when we move the roots, we say that below, so here we move root. So I think we also want to say below equals node, because if we have a new root, and then this is some tree, then the only 2 ways to expand are there. So we don't really care what's over there. But if we have a tree, and instead of adding a new root, we add down here, then we need this pointer still. So I think we only move below here. I guess like add right leaf. Okay, so 3. So now below would have went up to here. So now it'll say below dot right equals here. And then below moves here, right? Below dot right equals node and below equals node. Okay, I goes up by 1. So 4, this 4 actually gets added to visited. 4 isn't visited. So there's 2 places we could put 4 to satisfy the in-order traversal. We could put it up here as the new root, or we could put it down here. So because we have seen it before, so it's in visited. Okay, so it's telling us to move the root. I wonder if this is actually supposed to, because that means here we should have moved the root too, right? So I wonder if this actually just goes at the bottom. And then I think, okay, it didn't work. All right. Let me put some print statements. So print, let me say if node in visited, then we want to do this. Else we want to do this. And do we want to return above? Yeah, we want to return, because above is essentially the root. Okay, so 1, 3, 4. All right. So we'll say here node in visited, creating new root. Or I'll just say making node.val new root. Node not in visited, making node.val new rightmost leaf. Oh, wait. What am I adding? Oh, I'm adding values. Do I say that? Preorder of I is a value, right? So it's saying none of them are in visited, which is not true. Then I'll say here visited equals. So it looks like something's wrong with the visited set. Okay, let's try that. I don't need that. Okay, so we start at 1. So that should be in visited, no? Oh, was that what was causing it? Okay, let's see. So visited is 1. Node is invisited, so making 1 new root. So 1 is the new root. Don't need this. Okay, so making 1 the new root. Node not invisited, making 3 the rightmost leaf. Making 4 the rightmost leaf. Okay, and then the tree it's actually giving me is what? So that appears to be right, like what I want it to look like, but it's giving me 1 1 3 null 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 4. Okay, so it's right, except I think I added 1 for some reason. So when I make I see. So we actually do want it to be in order, but we want visited to be preorder of 0. Like that. Okay, there we go. Yeah, it's wasn't really expecting it to work all the way, but now at least we have some more test cases. Okay. So let's see here. So we have 3, 9, 20, 15, 7. And we have 9, 3, 15, 27. Okay, so start with 9. Three. So we create 3. So 3 is invisited, so we make it the new root. 15. Okay, and then we add, what do we add? We add 9. Alright, 15 is not invisited, so we make it the rightmost leaf. Like this. Add 20, so 20 is invisited, so make it the new root. We add 15. 7 is not invisited, so we make it the rightmost leaf. Okay, so I see the problem. So this algorithm does not 23, 7, 23, 7. So that wasn't even really what I got. Oh, well, I guess when you make it the rightmost leaf. So when did we add 20? Here. So it'd be like that, right? Yeah, okay. So I think what we have to do is check, instead of just if it's invisited, I think we need a more complex structure, or we need more information. So for instance, we need to know basically, instead of if it's invisited or not, I think what we have to do is say, does this have like higher root priority or not? Because 3 is the roots. But wait, for the other example, right, it was 1, 2, 3, 4. And 2, 1, 3, 4 in pre. And the tree is 1. So you start by doing 2, and then you add a root 1. Oh, because 1 is higher priority. So you say like, if maybe we can have a dictionary instead. So it's the value to its index and so like root order, and we set preorder so we can map each of these to its index or something like that. So generates root priority dictionary or something like that. And we can just say I equals 0 while I less than length. We could just say root index of preorder of I equals I. So if I print okay. So basically we want to check if the one we're currently checking has a if its root index is less than the current roots, then we make this one the new root. So this code is fine, but I just have to change some things around. So visited we don't need anymore. So now we're going to use a root index instead of just a visited set. So to determine, so it's just these conditions that are going to change. So node is the one we just created. So if root index of node val, so to move the root, it has to be less than the root index of the current root, which is above. And we don't need that. Okay. I think we want .val. Okay. So here, let me print root index. Make sure that's working. So 1, 2. Yeah, this works. Okay. So instead of node in visited, we could say node is higher than current root. Node is lower than current root. Hmm. So just some debugging here. Is lower than the current root above dot val. Okay. Node 3 is higher on the priority than making 3 new root. Okay, so let's see how this works. So we start off with just 9. Then it says 3 is actually higher, so we're going to add that. Node 15 is lower priority than current root 3, so we're going to make it the rightmost leaf. 20 the rightmost leaf, and 7 the rightmost leaf. So this is the tree I have. So 3, 9, 15, null. Wait, 3, 9, 15, null, 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 20, null, 7. Okay, yeah, so that's a good representation. But it wants 3, 9, 20. Null, null, 15, 7. Wait. Like this? Okay, so we both agree on 9, 3. So for 20, well, first we have 15. So I add 20 here. Okay, so this is the distinction. So in my case, I add, so let's duplicate that. So in my case, I add 20 here, but the right answer is to add 20 here and make your tree like that. So I guess in this case, what you want to do, okay, so I guess that makes sense. So you want to check and just make sure this is n, right? So we know, so does 20 have a higher, yeah, so 20 is a higher priority than 3. So because of that, we should put it like that. So I guess when we say add a rightmost leaf, we could also check, so below would have been 15, right? Yeah, it would have been below and above like that. So we can check if root index of node.val is less than root index of below.val. So if it's higher priority, then what we're going to do but the problem is, what if you have, because we want this to go there. So if we had, because this isn't always going to be above, right? Because we could have like 3, 9, let's say, I don't know, like 1, 2, 3, or 1, 2, 4. And then so we still, right now our pointers are above and below. And then we would have to let's say we get something that should go like this, like a new number. I don't know how we're going to make this one, because you can't go up the chain, right? Like you can't, sorry, my hair looks crazy. You can't go, you can't get this one from here. I mean, okay, so I'll solve it for this, but then when in this case, I wouldn't really know what to do. Okay, so if your if you're higher priority than the below dot value, then I guess I'll just say above dot right equals node, and node dot left equals below, and then below equals node. Otherwise, do this. Okay, yeah, but it's not gonna work. So I'm guessing that this is like one of those examples. 8, 4, 2, 1, 3, 6, 5, 7. I'll just write the beginning. Actually, let me just do in order. 1, is it just 1 through 15? Okay. So start with 1. 2 is a higher root index, so we like that. 3 has lower than both of them, so we're going to go here. 4 is the highest so far, so we'll make it a new root. 5 is the lowest. 6. So 6 is less than 5, so it's a higher root than 5. It is a lower root than 2 though. So it should go like this. Seven is the lowest so far. 8 is the highest so far. 9 is the lowest so far. 10 is just greater than 9. 11 is the lowest so far. 12 is higher than 10, 9, and 11. So if 12 is higher than 10, 9, and 11, then I think that means you go like this. Um, 13 is the lowest so far. So the lowest so far would go here, right? 14 is a little bit higher than 13. Don't want that. So 14 goes here, like that, and then 15 is the lowest. Okay, so this is my tree. So let's see if it matches the output. So the expected output is 8, 8, 4, 12, 2, 6, 10, 14, 1, 3, 5, 7, 9, 11, 13. Yeah, so I'm completely off the mark here. So I think we agree up until, let's see, 8, 4, 12. So I did 8, 4, and then 12 would have been, sorry, so 1, 2. Okay, so I did 1, and then 2, which is higher root priority. 3, which is lowest. Okay, so we're still agreeing with this. 4 is the highest. Okay, so still agreeing. 5 is the lowest. So I would put 5 here. So I think we're still fine. 6 is higher than 5. So then this becomes 6 and 5 goes here. So looks good so far. I can't really move this easily. Freeform. Okay, looks good so far. Next we have 7, which is the lowest priority, so I would put 7 here. Okay, so we have this part of the tree done. 8 is the highest priority, so it becomes a new root. Is this not what I did before? Why is 3 here? 3, wait. No, 6. Oh. I think I put 6 here, but it should have went here. I think that's the problem. And then alright, let's just keep going. 9 is the lowest priority so far, so it goes the rightmost node. Because, for instance, if you put 9 here, that would be incorrect, because if you do pre-order traversal, you will hit this before you hit this. But 9 in pre-order traversal is after, so it has to be over here. 10 is greater than 9 in the root hierarchy. So that means, and I'm just going to move this over a bit. So 10 would go here. So still looks good. And then do we get 11? 11 is after everything, so it's the rightmost node. Twelve is before 10. So I don't know how an algorithm, like, I don't know how you would do that. I think you definitely need a dictionary for this one. So for that, what I just did there is I said, okay, 12 is one space before 10. So that means it has to basically go here. And then you take whatever was pointing to it. I feel like this one would be easy if it was like doubly linked. Not easy, but like, so then that goes here. 13. So I look at 13. It's the greatest we've seen so far. So maybe you could have like a max that you've seen so far, and because it's a max, then it's the rightmost to leave. So this here is 13. 14 is 1 greater than 13. So that means you add it basically in the middle here. So I'm going to delete that, make it 14, and then you add 13 here. And 15 is the greatest we've seen so far. Okay, so that's actually the correct answer. I think I just rushed on this one and made some mistakes. So I do have an algorithm for it that I'm doing, which is at every step, you basically determine the relative priority. So if it's the highest index that you've seen so far in preorder, then you know it's the root. You want it to slot in between. So you basically want to find the next minimum root and then add it like right above that, I think. So for instance, when we had 8, 10, 9, 11, and then we get 12, right? So 8, 9, 10, 11, and then 12. So the next spot, so the next least like priority root is 10. This one. So like 1 to the right is 10. So that means we basically replace this with 12 and then make 12 left pointer go to that. That's what you do. And then for 13, so 13 is the maximum that we've seen so far. So maybe if you check the one to the right and you haven't seen that one before yet, then you know you just add it to the right. So that was 13. So 14. So we check the one to the right and we see, no, wait, this should be 13. So we see 13. So then we do the same replacement mechanism. Okay, so I think I figured out the algorithm for it. I just don't really know how I'd go about coding it. There's just a lot more to figure out. Maybe you could do a dictionary that's... I just don't know how you'd store all of that information, because you would have to know for every node it's what's pointing to it. I guess what you could do is have a dictionary where you have a value and you have its parents. And you can use that somehow. I don't know if there's some array trick or something. But yeah, this one, I'm not sure if this is the right way to go about it, but I think like if you gave me these numbers and I had a whiteboard, I could draw the tree. But in terms of coding it in linear time, I'm a little bit stuck. So I think I'm going to call the video there and look up the solution and see what I can find. But anyway, thanks for watching day 19. I'll be back tomorrow with day 20.